All right, so we're talking about graphing today here, and this is a website and how many hits it's getting. Do you see those spikes? Those are days when they paid for advertising, and all of a sudden, boom, they get tons more hits that day. And all of a sudden, a website might start selling a lot better on a certain day. Well, it's probably because their marketing manager just put out an ad, and all of a sudden, people are coming to visit. I remember when my website got featured on a TV show once. It was on like the Today Show, some morning show. I got an extra 4,000 hits that day, more than usual. So it does actually, you can really see spikes. Well, this one levels off the spikes, and so you can't see them anymore. Do you get how when I did that, I lost information? As the owner of the company looking at this, I'm not getting as much out of this because I can't see those spikes. I still have time on the bottom, and I still have hits on the vertical axis. The time is always on the bottom in these. Have you noticed that? Time is pretty much always on the bottom of a graph. And that's because it's the independent variable, and that's where the independent variable is supposed to go. Time should always be on the bottom, not because it's special, but because it's the independent variable. All right, this one's kind of a combo deal where you got both the smoothed out and the spikes, and those spikes are important. You want to know if you're spending money on advertising, whether it's actually bringing in more hits. All right, so what is the real world meaning of this graph? Number of the people in the stadium versus time. It helps me to think about points on the graph, like that point right there. Do you get that's at the very beginning of our time that we're checking? So that's right when the game ended. Do you get that it's fairly high? So what's that trying to say? There's more people in the stadium, a lot of people in the stadium right then. And then at about 20 minutes after the game, there's nobody at this point. And this is, let's say, 10 minutes after the game has ended. At 10 minutes after the game, there's still a bunch of people in the stadium. Now, is this realistic? Do they actually leave in a nice straight line like that? No, probably not. I would like you to try to figure out if you think it's more likely to be like this, the red one, like this, the black one, or like this, the blue one. And I'd like you to sketch it on your iPad and tell me which of those is most likely. And maybe you should add in something that's not on my graph to make it more real world like. What do you think would be better? The red one, the black one, the blue one, or something that you make? Give it a shot right now. Sketch it. Might have to add some. Might have to add a piece of paper, otherwise this is like the 5th slide or so. How many chose the red option? How many chose the blue option? Okay, now it really depends on your perspective. I am going to show you what I would have done. I would have done something like this. Right after the game ended, I would have just a little flat spot, just for a little bit of time, where nobody has actually left yet. Do you know why? Doesn't it? If you're talking about this is not about leaving your seat. What is this about? Leaving the stadium. Wouldn't you agree it's going to take some time before you could actually get to the door to get out of there? All right, I know this is getting picky, and that's true. Some people left, well, heck, at the Vikings game the other day. They all left after the 3rd quarter. They were all gone in the 4th quarter. Anyway, so at first you're going to take a little while to get out of your seat and to the door, and then all of a sudden there'd be a bunch of people at the beginning. Would you agree it's pretty steep at the beginning? That's a bunch of people leaving really fast. Okay? And then most people just kind of like try to leave in a somewhat orderly fashion, and then what happens at the end? Why would there just be a few people left in the stadium? These are human beings in the stadium. Do you think like everybody walks out and like 10 minutes later it's completely empty and there's like crickets chirping in there? Isn't there a few people walking around? Maybe it's like they're players, or they're trying to hopefully get autographs or something. Maybe it's people that clean the seats. Maybe it's the vendors that are cleaning up. Maybe it's the security people. But there's going to be still some people in there. So I think if you really think about it, the graph could be more complicated than just a simple straight line. All right, moving on. Independent versus dependent. The ultimate independent thing is time. Time is independent because you can't stop it. It doesn't depend on anything. Think about that. If you're independent, it means you don't depend. If you were completely independent from your parents, then that means that they could disappear tomorrow and you'd be fine for the next 2-3 years. Well, eventually you might realize, how come these people are coming to take away the car in the driveway? How come there's no food in the fridge? Well, because maybe mom and dad were taking care of some things that you weren't taking care of. Now, of course, most of you in other countries could be married by now, so you could be independent. You could be like off on your own, living, having your own little family in some other country. But in our country, usually you're going to stay dependent, even though you could be independent right now. All right, well, let's talk about dependent. The ultimate dependent thing to me is money, because how much does something cost? What's the right answer to that? It depends. For example, if I say, how much does a watch cost? What's the right answer to that? The right answer is not $400. The right answer is depends. Depends on the quality. Depends on where you're buying it. Depends on, all kinds of things. How about this? How much does water cost? Depends. Because if you're at home, tap water is not free, just to clarify. It is almost free. It's like 2 cents a gallon when you buy it from the city, your tap water. You have to pay for that water. Okay? But when you add it up, there's lots of gallons running through your house. You actually have to pay a decent amount for your water bill at home. But when you buy your water at the grocery store, it's like 15 cents for a bottle. That's not a gallon. If you buy it by the gallon, it's not that much more expensive, actually. It's like 35 cents for a whole gallon, depending on the store you're at. But what if you go to our cafeteria? How much is the water there?
Like $2.
Is it 2 or I think it's 1? Isn't it 1? Who's actually bought a water? Is it $1? Okay, it's $1. $1 for the water here. And then what if you go to the Twins game? Is it still $1? It's not 7. It's probably 3 though. It's probably like $2 or $3 for a bottle of water. All right. So how much does water cost? It depends. That's why this is dependent. Get it? Independent is down here, and the time is the ultimate independent thing because nothing can stop time. Time doesn't depend on anything. It just keeps going. The only thing that ever stops time is if you're traveling at, if you travel at light speed, time theoretically stops. All right. You weren't with me. Stay with me, please. All right. So I want you to be at, are you? Really? So I didn't see anything else on your screen and it's not changing right now to something else? All right, anyway. Oh, you're researching stopping time. Well, that's kind of cool. All right. Well, the only way I was saying before that you can stop time is if you travel at the speed of light. Picture this for a second. You get into your spaceship and you launch out looking for this planet they just found. Have you heard about this? There is a planet that is drifting through space. Normally, what do planets do? They orbit. What? A sun, a star, okay? This planet is like that one they've never seen before. It is drifting through space. It is not orbiting anything. It is just traveling. Normally, planets don't do that. Okay, asteroids do that, but planets, whole planets, don't usually do that. So we could actually have a whole planet decide to just be on course to hit the Earth. Can you imagine that? This planet, if it isn't heading towards us, but it could be. It wasn't. But this planet just is drifting along, and it's like the size of Jupiter, and it's a gas giant like that. So it's drifting out there in space, just drifting. Okay. So anyway, if I'm doing independent versus dependent, and I'm traveling at the speed of light, I get in my spaceship and I'm going to go to this really cool planet and study it. If you travel at the speed of light, people have always worried that it's going to take you so long to get there, you're going to die on the way. Isn't that a crazy thought? To get to this planet, it's 80 million light years away. That means if traveling at the speed of light, it'll take you 80 million years to get there. Isn't that insane? If you could travel at the speed of light, which is insane enough, It'd take you 80 million years to get to this planet, and that's if the planet doesn't change where it was between now and when you got there. And it's moving the whole time. So it's a moving target. Well, the only good news is that when you travel at the speed of light, you don't age because time isn't changing. Isn't that insane? The thought that if you're traveling at the speed of light, time is not changing. If time is not changing, you are not aging.
So if you can get there in 0 seconds?
You would get there, no, you would get there in 80 million years, but time hasn't changed for you.
Oh, but it would,
Time around you has changed.
it would suck.
It would suck. It depends on if you brought a couple movies, nice. Can you imagine watching Forrest Gump for the 9 millionth time? All right, anyway, let's move on. Independent versus dependent. Of these two, I can guarantee you one's always independent. Which one's always independent? Time, good. And if this is independent, then this one's dependent. Temperature must be dependent on time. Think about this for a second. If you knew what time it was, would you be more likely to know what the temperature is outside? That it generally gets warmer as it gets in the afternoon, and then when it gets to be nighttime, it gets colder again, and then it cycles through. All right. How about this? I think it's easier not to think about which one's independent, but to think which one's dependent on the other one. So which one depends on the other one here? Ice cream sales depend on the temperature. Think about it. Dairy Queen even closes in the middle of the winter. A lot of the smaller Dairy Queens close in the wintertime. That must mean that they don't get as many sales in the winter. Would you agree? That's why they would close in the winter. All right. All right, moving on. Cost of food versus location. Which one depends? Does the location depend on the cost of food? The location changes based on how much food costs. So I walk up to something and it's really expensive. Oh, I must be in China or whatever, wherever it's really expensive. No, it doesn't change. The cost of food will change. So this one depends on the other one, and this one therefore is independent. The cost of food depends on your location. If you want to buy a hamburger and you are at McDonald's, it's going to be $1. And if you're going to go to the Twins game, it's going to be like $9. Of course, it'll be a better hamburger, but okay, moving on. Increasing versus decreasing. Would you agree that this one is increasing? But if you really think about it, if you read it this way, isn't it decreasing? It all depends on which way you think about it, right? But which way do we always read things? From left to right. And this would probably freak you out if you were from a country that reads from right to left, because there are countries that do that. Okay, but we always read from left to right. Can you name a language that reads from right to left?
Oh, yeah.
I believe in Chinese and maybe Japanese both. It's from right to left. All right. This one is decreasing. But we're going to be expecting you to know more than just that in a minute. We're going to be talking about how it's decreasing. But for right now, just as you read from left to right, increasing or decreasing, this one can be very confusing. Is it increasing or decreasing? Or is it both? Okay. Now, some people would argue it's increasing the whole time because of those arrows. I don't agree, though. Because in this part right here, it's going down as I read from left to right. Who cares if there's an arrow? If I read from left to right, it's going down. That's decreasing at the beginning there. How about this part right here? What's it doing there? It's increasing. So it's decreasing, then it's increasing. All right, the last one is different than all the others. Why is it different? It's decreasing, but why? Why is it different? It's decreasing at a constant rate. Very good. It's decreasing at a constant rate. So this is about rates now. This is increasing, and notice it's not curved. So it's increasing at a what? At a constant rate. What's that? Decreasing at a constant rate. Notice how we're having to describe two parts each time now. So first you say it's increasing or decreasing. Then you say whether it's increasing at a constant or increasing at an increasing rate or increasing at a decreasing rate. You always say it twice now. This one, is it increasing or decreasing? It's increasing, except for one little zone right here where you could argue it is not increasing. It is what? Staying the same. It's called constant. All right, now how about this increase right here? It's much steeper, so it's increasing at a faster and faster rate. We'll talk about that in a second. This one, would you agree it's decreasing?
No.
But decreasing at a what?
At an increase.
Exactly. It is decreasing at an increasing rate. How do I know that? Because at the beginning it's not very steep. And at the end it's steep. The steepness is the rate. Would you write that down? Steep equals rate. It'll help you remember it. Another way to say that is steeper equals faster. Steeper equals faster change. It's getting faster and faster if it is steeper. If it's getting steeper and steeper, it's getting faster. So steeper is faster. All right, so this is not very steep. So it's decreasing, but it's decreasing not very fast. Here, it's decreasing very fast. So this is decreasing at an increasing rate. How about this? Do you agree it's increasing? Increasing at a what? Increasing rate, because it starts out slow, ends up medium, and fast. Okay, so how do you demonstrate the following changes in a graph? If it's increasing, it's going up as you read from left to right. If it's decreasing, it's going down. Slow change. Is that steep or not steep? Not steep. Fast change. Steep. Constant. If it's no change, yes, and another way to say that is it's flatlined. Have you heard of that before? If you flatline, that means your heartbeat, which is supposed to be doing ba-boom, ba-boom, just goes me flat. All right, so flatlining is constant, no change. All right, when should you use each of the following? A straight line, if it's constant. A curve, if it's increasing or decreasing. At a increasing rate or a decreasing rate. If it was at a constant means flat or straight. What is the difference between constant and constant change and constant rate? Do you agree that sometimes increasing, sometimes decreasing? Do you get the fact that it's straight lines means that this rate is actually staying the same? It's just either increasing or decreasing at the same rate. Okay, so the difference between constant change, this is constantly changing, as opposed to a constant rate. This rate might be like 7 miles per hour that you're going. Okay, and this was 7 miles per hour except in the other direction. 7 miles per hour again, 7 miles per hour, so my rate's staying the same. But it's just the direction that I'm going. All right, moving on. Increasing at an increasing rate. Make me a little sketch and show me, is it like this or this or this? Make me a sketch of increasing at an increasing rate and then turn it so that I can see your answer on your iPad. I'm going to pause while you do that. Saw some that were straight lines, saw some that were more curvy. Here's what it was supposed to be. Increasing at an increasing was like that. Increasing rate means that it has to start out kind of slow, not very steep, end up kind of fast, very steep. Okay, increasing at a decreasing rate is like that. As opposed to increasing at a steady rate, which is like what? Straight line, like that. Any questions on those? All right. That's one of the main things you need to get across. And we've already talked through all of these, which is just fine. Oh, just plain constant, I want you to get that. Do you know what just plain constant means? It means a straight line, flat line. That is constant. It is not changing at all. Okay, so constant again looked like, that's constant. That's different than a constant rate. Here's a constant rate of change. You may be going 7 miles per hour. So your distance compared to your time, that's a constant rate. This is just constant. Okay. Description of this graph. All right. See how it's kind of steep at the beginning? It's moving, it's changing, right? So let's say this is distance and this is time. I get my distance is changing here. And all of a sudden I am 8 miles away from home. But then all of a sudden, what happens? It changes and becomes what? Constant. What does that mean about me on my trip from home? I'm staying the same distance from home. I am staying at 8 miles from home. Is time changing? Yes, time keeps on changing, but my distance hasn't changed. There's one more outside the box thing that could be happening. If I was on a bike trip and I went, okay, my bike broke and I'm stuck in one spot. I am stuck at 8 miles away from home and the time is changing. But think even further outside the box. How could you be staying the same distance from home? Yes? Very good. You could be going a circle around your house. Think about this. Here's your house. Here's you. And you rode away from your house, and then all of a sudden you start doing this. You're staying at the same distance from your house. Very nice. That could be what's happening. Because then your distance, 8 miles away from home, is staying the same because your radius is at 8. Why would you want to do that? Maybe just to mess up the person who's GPS tracking you. Mess with their head. Okay. All right, domain and range. Domain is the X. Range is the Y. You can get those two just through your head right now, that the domain is the X's and the range is the Y's. That would be really good. So which one's independent, domain or range? Domain. The X stuff is the independent stuff. If you were graphing it, it's like this, and this is independent, and this is time. And this is dependent, and it's Y, and the ultimate dependent thing, money. Now, it doesn't have to be money, but money is a great example of something that's always dependent. It doesn't have to always be independent, like time. Time has to always be independent. Money doesn't always have to be dependent. It can actually be the independent thing in certain circumstances. All right, now let's look at this school pop machine. They are complaining that basically the pop machine runs out of pop. Ooh, big surprise. You take enough cans of pop out, it eventually gets empty. Look at the graph here. Do you get how it starts the day full? Does that make sense? And nobody takes any cans out until what happens? People get to school and they start drinking pop. Okay? And then all of a sudden the level of number of cans in the machine drops to a low point, and then all of a sudden what happens? That's being refilled. Very good. And then it stays like there's nobody drinking it or using the pop machine for a while. And then all of a sudden it gets super crazy steep. Why would that happen? Lunch. And then they refill it again. And then some more people drink some. And then, oh, another big dip. Where's that? Right after 3 o'clock. What's happening there? School just got out. Makes sense. People will drink a lot of pop. It's empty for a while. Kind of annoying. We don't know how many people went to the machine when it was empty either. So can you see how a lot of people complain about the machine being empty even though it was only empty for a short time? Because if you only have this one little time zone before you get on the bus or before you go to your activity where you want to get a can of pop, maybe the machine's only empty for 15 minutes, but literally 100 people could be not able to get a pop. So do you get how that could... One person could argue the machine's only empty for 15 minutes a day. And somebody else could say, tons of people are being inconvenienced by the machine being empty. It is possible to be both. All right, moving on. I think it just answered all those questions right there, except for this one was kind of interesting. Did you know there's actually laws about what can be in the pop machine? Like Minnetonka could actually break a law by selling certain kinds of pop in the pop machine. It's illegal to, because there's too much sugar, basically, and not enough nutritional value. So get things like candy bars don't have any rules because they have some nutrition. But things like gum, which has no nutritional value at all, can't be sold. So they say. Again, there's different rules in different parts of the building where you're selling stuff. Like they can sell stuff to teachers in the teachers' lounge. You know, we can have like big vials of fat if we want to, but you guys can't. Yummy. All right. Anyway, moving on. This is an important concept, discrete. A discrete graph is more accurate for cans of pop because can you actually have anything between 89 cans of pop and 88 cans of pop? Is there anything in between there? No, so therefore they should be separate points. If you're buying shirts, you can't buy, I'm going to get 1.7 shirts today. No. You're going to either get one or you're going to get two. All right, so these are separate points. Notice if I connected them, I'm implying that there are things in between them. There are not. There's nothing between 89 and 88 cans of pop. So you can't draw a line through all graphs. A lot of people think you can. You can't. This is called a discrete graph with little dots, and they can't be connected by a line, because otherwise you're saying there's something in here. There's something between this and this. There's nothing between like 89 and 88 cans of pop. All right, moving on. This one's always interesting to me. Would you please make me a little sketch of a hot drink sitting on your desk? And you've got to figure out if it does this and then this, or if it goes like this and then this, or if it's more like this and then this. So, you know, figure out what do you think a hot drink's temp versus time would look like. You're going to sketch it, you're going to show it to somebody else, so don't make something you're embarrassed about. Make it of high quality. All it needs to be is a simple line, but think about it. Make me a little sketch. I'll pause while you're doing that. Okay. I'd like you to turn and show the person, and I'll show you which way you're going to show, you two aisles. You don't have to slide your desks together, but I want you to show yours to each other. You two rows. Okay? Your two rows. Same deal. You two are going to work together with him. Slide over. In the back, you're going to look across at I am in the green shirt. Okay. You two rows, look across at each other and see if you're the same. Explain yourself. Argue. You don't have to argue if you have the same answer. Okay, now you have to make a decision. Are you right or is the other person right? And don't just think you're right because you're you. Maybe they have a better argument than you. I want you to choose. Is it more like, at the beginning any of the graph anyways, is it more like A, which is like going down really steeply, B, which is constant, or C, one of these is, all these are decreasing. Would you agree the temperature is going to decrease? If it's really a hot cup of coffee, unless you're sitting in a room that's like 5,000 degrees, in which case the coffee would go up in temperature, which is weird to think about. Of course it's going to go down in temperature in a normal room. So is it A, B, or C? I want you to pick one. Is it more like A, more like B, or more like C? Write it on your iPad and turn it my way and zoom it in so I can see if you're an A or a B or a C believer. All right. I'm seeing one B, I'm seeing lots of A's, and I'm seeing a few C's. All right, so some of you are right and some of you are wrong. Now, if the temperature, let's think this through thoroughly here. If the temperature starts off at like 104 degrees, okay, for this coffee, and the room temperature is like, let's say, 70, do you agree there's a big difference at the beginning? And do you get that the coffee is trying to get itself to what? To room temperature. All right. So should it increase faster at the beginning? Or should it start out not getting cold and then all of a sudden get really cold really fast? All right. So it is more like A. It should decrease a lot at the beginning. Now, at the end of the graph, though, did any of you have this part right where it should level off? Because that's room temperature. Good thinking. If you had it leveling off, no matter how you did it, that's good thinking. At some point, it's going to hit a temperature with same as a room, and then it won't change anymore. Okay, good. Let's move on. Your assignment for today. Let's get there. It's called interpreting graphs. So it looks like this. And I shouldn't just give you the answers. We should look at them together. It's called 4.1 interpreting graphs. As you're looking for it, you're looking for the folder for functions. You're looking for the first folder called number sense, I think it has on it. And then it's 4.1. Today's date is 10-14. Anyway, if you find it, it looks kind of like this. This asks you to sketch something that's increasing throughout, meaning it has to start low and end high, but how it gets there is the important part. It says first slowly and then at a faster rate. Remember, faster means steeper. When it says faster rate, it means steeper rate. So it starts out slow, meaning not steep, ends up steeper and steeper, so it's like that. They could have said that as increasing at an increasing rate, but you have to understand it if they say it in different words. Okay? This one says decreasing slowly, so hopefully you start off decreasing not very steep, then more and more rapidly, steeper, 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 suddenly becoming constant. Flat line. That's constant. The word constant can mean constant change, or it can just mean constant. Since it just says constant, it doesn't say constant rate. Constant means like this, flat line. Okay, this next one does confuse people sometimes. It says it doesn't have any sudden changes in rate. If it's increasing and decreasing, let me give you a hint. That's increasing and decreasing, but are the changes sudden? Yeah, those are sudden changes. It says without any sudden changes. So this is the wrong answer. Okay, I'm going to leave you to work on that yourself.